Okay, I think that we can get started. Welcome everyone. I think if I get it right, this is our 12th meeting, but 13th in the schedule. So as I understand, we have only one meeting. Yes, you can confirm. Okay. So we have one meeting next week, and then it's just about communication grading and other stuff. Yeah. So like for me, this week went surprisingly fast. It passed away like it not existing. So so of course I'm referring to the lack of those grades for the last two assignments. I will fix this before the next week for sure. Yeah, and so for the next week, I propose that I will not bring any new material because it's just a little too late. I think that you have many other responsibilities, including some exams and similar things. So I propose that today we'll code what we are to code to to just prepare everything for you. Yeah. And for the next week, I propose that we'll meet here in room and online and discuss all the issues that you might have. Firstly, with the last assignment, and then we can also discuss the previous ones if you still wanted to take anything out of it. Yeah. So of course, I suppose that if you will have some questions, you can ask them earlier on the email. So I will try to prepare some answers, maybe also for everyone uh, about anything related to it. If not, then we can discuss this more on the standard basis. So I also propose that I think that I will try to organize this meeting in some Teams or Zoom rather than streaming this in the YouTube. Yeah, so for especially this is to online participants. Uh, so any objections or doesn't sound fine? Okay. So if we will have any kind of issues with programming or whatsoever, yeah, we can then discuss them. Uh, yeah, okay, perfect. So today we'll continue this dynamics of mechanical systems. Yeah. So here I have, like usual, those PowerPoint presentation, but it's nothing new. I just brought to this presentation this one slide that you have already seen. uh, Simply because of what is written here in MATLAB, that our next step is to prepare G vector. Yeah. Again, you can see what is here on the screen. Yeah. So to prepare G vector for rotational joints. Yeah, because this is what is needed for our pendulum. That it's still not here. We haven't defined any joints here. Yeah, because we went just for inertia and for some gravitational forces. Yeah, so we haven't implemented yet the equations of motions for dynamical systems. Yeah. Uh, Okay, we have implemented them, sorry, but we have implemented them only for the system without constraints. So now we have to go with the constraints, and the missing part from here is G vector, because the rest we still have to put all this together somehow. Include alpha, beta in the system, generate equations of motion, solve equations of motion, yeah? So let's see, maybe it will go really fast. And then just let's see, yeah? So G vector, yeah, I suppose that you have done it for kinematic analysis, at least some of them, yeah. I hope, yeah. Uh, so how to do this? How you would proceed from this point? It's not a tricky question, yeah. I hope, yeah. Mm. Mm-hmm. Yeah, but how to implement this? I'm now talking about technicalities. Yeah, so in the report I ask about no technicalities, but here we are at the programming session. So now I ask about technicalities. So how to do this technically? Yeah, because yeah, we have here equation. Yeah, we know that g for g for simple constraint is 0. We know g for driving constraint is just second derivative of the function with respect to time with appropriate sign. Yeah. For transactional joint, then you have to calculate it. It's a little more challenging, but nothing too crazy because still this joint this is one part of this transactional joint. Yeah. With this d vector, if you correct points, and another one is just a times v local. Yeah. So and just you have that product of this. Nothing too crazy. A little more complicated, but I don't think that is something super complicated. Okay, but maybe you didn't. Okay, exactly. So at least to implement the G vector, I would just copy paste constraints function because it's similar, or constraints dt. It doesn't really matter. But I would go with the constraints because in constraints dt we already has missed some parts. Yeah, I wouldn't go with Jacobian of the constraints simply because Jacobian of the constraints is matrix, and this is vector, and G is also vector. Yeah, and it will have exactly the same structure. So to copy it, change it name, like something constraints G. Yeah, nothing too crazy. Or G vector, because then this name look with G it looks too similar to others, so it's not exactly what I like. I will fix the name to fit the name, and of course we should get consistent at least with this comment. So typically the fewer comments the better. If you can return the vector of the uh, yeah, so it's something like this, and then we could just call it G because why not? And it is the number of the constraints, and we have now fill the missing part. Yeah, here. So as we discussed, G for simple constraints is just 0 because it's only acceleration term. Yeah, there is nothing left, so we can just remove this. Uh, and now for the revolute. Of course, indices are the same. So this is nice in the approach that you have chosen, that here nothing changes. And now we have just implement this part. Yeah. So AISI. So AISI is here. So of course this part also disappears. And now we need that one. So we need velocity. Yeah, so we need angle. Of course, this angle we need to generate AI. But now we need velocity to write this equation, so we provide this information. So it's missing clearly. Yeah. So for G to work, we need Q dot. Yeah. Also provide Q dot. Uh, this is not really needed, I think. It should be. It should. Yeah. Uh, same applies to that one. Yeah. But instead of that one, we need. Of course, velocity of our angle, so phi dot I, for example, and then we can get from q dot of the very same index here, because the all the in the coordinates must go along the velocities and along the accelerations. Same applies here, because we will need velocity of j. It's also omega. Yeah, it's the same like omega vector on the planar case, but naming is naming, and we have to get it from the velocity vector. Okay, so now we have velocity, so we can write the first term that it's rotation times at and simply times this square. Yeah, so like exactly this equation. Yeah? And now we have to provide also that one. So this is going away. This is what we are left minus rotation matrix times Sj local and times uh, rotational velocity of or the square of the change of the vector of, of the angle. Yeah, and well, that's all. Yeah, so it should already work. Yeah, so I think so. Nothing too fancy here. Uh, here we have to work a little about these driving constraints. Not that we will use them, but you know, for the dynamical case, but to make it complete, I think that it's not a good idea to skip it. If I want to skip it, I have to put here some error, yeah, that warn us, because you know, this is one of the worst cases that we try to use it. We haven't implemented this and then it's not working, and why? Yeah. So it can cause logical error. So either we have to put here error message that implemented in the future, or we can implement it. So I suppose that let's implement it. Yeah. And it should be pretty easy because we already provided coordinate acceleration here. Uh, that it's needed, and it should be like that. Yeah. So because as discussed during the lecture and discussion of how to make this g vector, yeah, second time derivative. So we add here to dd, and instead of coordinate, we get coordinate acceleration, and then change of the sign because it goes to another side. So that's why I have removed this minus. And that's all. Yeah. So now we have working implementation of the G vector. Questions? Well, technically it would be nice to test it, but we will test it soon. Yeah. Uh, or it's better to test it. Yeah. So let's just test it. So that it's just shorter. Constraint G vector, and we need system. We need Q. Do we have Q? Not at this stage, but it will be Q0, Q dot 0, and 0, 0. So for this to work, we need at least that one. We also need Q dot 0 with zeros of size of Q0. Clearly something is incorrect because we get G as empty matrix, so something is clearly incorrect. Okay, maybe because we don't have constraints. So yeah, so it makes sense. Yeah, from that perspective, it makes sense. Yeah, so we haven't added any constraints to the system. So yeah, so before we can do this, we have to fix, and we need one more point. Complete definition of the pendulum system. Yeah, so we have added here a body, ground, and second body pendulum. Yeah. Okay, and here we note we assume that the initial value of the coordinates may not be exact. Okay, and so we have to account for it. But here let's complete. So add. Let us add the joints. Yeah, and we have to add what the joints to the system to make it working. Yeah. So following the slider crank, okay, we will copy paste that part for sure because we have to add simple constraints for what? For the ground, of course. We need to provide simple constraints for the ground. Then we have to provide this revolute joint, yeah. So let's find here some nice definition of the revolute joint. Here is one ground crank, yeah, it looks nice. And it's not between ground and crank, but it's between crank and pendulum. Yeah, 0, 0 is correct because we'll put it at 0, 0 at the ground. And I believe that somewhere we had definition of our system. I think this is the correct one. Yeah, so we have this definition. So we assume that our pendulum has length of around, not around, has length of 100 millimeters. Yeah, and this is how our local coordinate frames looks like. Yeah, so in the local coordinate frame of the pendulum, yeah, the local vector that indicates the location of our revolute joint is just minus 50, 0. Okay. Okay. Is it? That's all. But now we have this node. So, but okay, okay. Let's first add those joints to the system and check G vector. First things first. Yeah. Run this, run this, run this, run this, and now we have G vector that has 1, 2, 3, yeah, correct number of the entries, yeah. So of course for the simple are zeros, and here are zeros. So do you think those zeros are correct? Do they look correct? They are correct. And simple reason for this is because of those terms, yeah, that velocity currently is just 0. Yeah, so there is no, yeah, so if velocity is 0, it doesn't matter what are other stuff, yeah, it will be always 0. Yeah, but we want, okay. velocity is zero because we assume that initial velocity is zero. Yeah. Yeah. So this is this is this thing. We also you're referring to applying driving joints that of course makes everything moving. Yeah. But in dynamics, typically we don't have driving constraints. Yeah. Because we are rather consider what kind of forces or torques applied to the system will make it moving. Yeah. So here so and then just if we are just solving this kind of dynamical analysis, the initial velocity is just characteristic of the system. But let's now assume that everything has velocity 1. Yeah. Maybe it's not the best assumption for the ground, but okay, just for the purpose to see if this provides us something else than 0. And yeah, of course, here is 0 because, yeah, it doesn't depend here on the velocities, but those values are clearly non-zero. Are they correct? Hopefully, yeah. We implemented, the questions are pretty simple. We implemented them. Uh, and yeah, to verify them, of course, we can once again, run some kind of analysis, yeah, or use some numerical methods. Yeah, ooh, but in general, by looking on this, at least we know that there is some implementation. Implementation is working. It looks correct. Yeah, we cannot be 100% sure, but let's assume that it's correct, like usual, and proceed. Questions, suggestions, whatever. Okay. So we have G vector. We have complete definition of the pendulum system. Uh, we also have to solve at some stage. We have to also solve the system to get to make this node working. Yeah. So because we assume that here we just put some values that make some sense, but are not necessarily super accurate. And of course, if we calculate now constraints of our system, they are not met. Yeah, so this is not the nicest point where that we can start our solution. If the constraints are not met, it simply means again that the pendulum is disjoint from the ground. Yeah, so it's just located somewhere like here, for example. Yeah, so not the best. Uh, so how to do this? How we could get c equals 0? Yeah. Well, how to do this? Yeah, of course. This is the idea, but but how to do this technically? Yeah. So the description is nice, but how to now any ideas of how to code it? Okay, so first of all, we can notice that we have already done it in some way because okay, have no electricity because of some reason. Okay. Uh, so yeah, technical stuff, yeah. But okay. Because this is in practice, this sounds a little like solution for the kinematics on the position level, yeah. That we want to get solution constraints equal to 0. Yeah, because this is the definition of the kinematic solution for the position level. The issue here is that we cannot use directly those methods. That is not easily, because the number of constraints is not equal to the number of coordinates. Yeah, so we are missing one condition, and the reason is that it's just pendulum. Yeah, so it can freely rotate. So it has 1 degree of freedom. It's clear. Yeah, if you apply the gravitational force, it will move according to that force. Yeah, so it's free to move. So to get it, to solve this, yeah, so solve this equation, we need to provide one extra constraint. Yeah, uh, like everything, I tell this too many times that it can be solved in many ways. Yeah, but the one way I can see that should be pretty straightforward is to add constraint, driving constraint with zero velocity and zero acceleration, just telling what angle we are expecting to get. Then we can just solve our system kinematically on the position level like usual to get our Q that will match our C, because if it will match also those equations, and then we can remove this constraint from our system. Okay, does this sounds like a plan? So let's see, and let's try if we can effectively do this. Yeah. So we want to get consistent Q0 that is consistent with our constraints. That the Q0 at this time that will makes our constraints to be equal 0 at the start. Yeah. And to do this, would it be useful if I write here this procedure? Okay. So here is written this algorithm in just a few steps. So I add this driving constraint. So let us add driving constraint. Yeah. So we will want to add driving constraint, of course, to our system, to body called pendulum. Constraint coordinate is phi. And coordinate function. So we want only coordinate function to be valid. Yeah. So just we will provide some specific value. So we want this is function of time, because we assume that this is function of time, so it will provide some time. But we wanted it to be, let's say, minus 31 degrees. Yeah, like it was here. So minus 31 degrees. We are still missing coordinates, velocity, and acceleration. Yeah, so and we assume that we will provide it. But simply this returns 0. And of course, then if velocity is 0, acceleration is also 0. I think that we assume 30 degrees. Minus 30 degrees. We can even put it horizontally, but let's start with something that is close to see that it works. Yeah, so add this driving constraint to the system. And now what? So now just the system should have full rank. Yeah, because now we have 6 coordinates and 6 constraints. Yeah. So now we can just solve it for kinematics. Yeah. So we have already done it for the slider crank mechanism. Like here and like here. Yeah. So we can just copy paste this line. That our Q0 that we wanted. We'll solve for constraints. We have already this Jacobian because this is already done. We'll have Q0 that is already was provided here and some tolerance. We can do this, of course. We can do this that way, and let's see what happens first. And like here, we provide this short this error message if iteration counter that must be larger to 0. Yeah, and in practical, the meaning is the same, that we wanted to get kinematic solution on the position level that works. Yeah. We get some errors because we get unrecognized function of variable t. That it's here because we haven't written that t is equal to 0. Yeah. Okay, and now we get a message that kinematic solution on position level for t equal to 0 works. After fixing our error, we get new Q0, 3 numerical zeros, which is this is pretty expected, and some values here. Yeah, and we get okay, a little too many. So it's solved despite the system is over defined. And why we get, do you know why we get too many entries here? Any ideas? Okay, so I know why. Simply because here I provided this sys add constraint sys, yeah, and because firstly I got the error in this cell, yeah, I didn't run it from the start or like I should, and because I ran this cell twice, I get here Darby constraints, add them twice as well, because the error was later. Does it make sense? That you, so I wrote this code, yeah, they haven't provided t, So it runs, but it throws an error, but it throws an error somewhere after this line. So it add constraints, tries to run it, throws an error. Yeah? Then I fix the error, but it again ran into this line. So it added the constraint again. Yeah. So that why those two are the driving constraints, the same driving constraint. Yeah. And MATLAB works because MATLAB works well with the matrices that are not square, which is nice sometimes, but not necessarily nice because like here it's not something that we wanted, yeah. Because it's possible to, as you may know, solve the system when the matrices are not square. Yeah, then you have to do you run into some different type of algorithms, but it's still doable. And as you can see, it solved it nicely. Yeah. But let's fix it. So I will just comment out this part for a while and run it again and put here deadline to see constraints. And I think that I change as well. Yeah, constraints at time 0. Yeah, and now it's correct. So because I have clear at the start, so it clears all the variables and define everything again. Yeah, so now it works correctly. Because I was a little surprised that here are non-zeros. At least not real zeros, but only numerical zeros. But I suppose that because it's solved in some last square means, yeah. So not that why those artifacts appeared because of different numerical procedure. But okay, now it's fine. Yeah. And now we have to proceed with the third step. So we have to remove driving constraint. And how to remove driving constraint? Simply, we can set the sys constraints driving to empty array. Yeah. So we can set. So now we'll just set sys constraint driving to empty array exactly as it's written here. Yeah. And now we can check it again. So I will just run it here. Okay, I could run the full code. It doesn't really matter. Yeah. Okay, yeah. And now it works. So now we have 5 constraints and all of them are equal to 0. Yeah, and we have our correct Q0. Does this make sense? Good. The issue is that we now introduce some mess. uh, because here is something, here is something, and so it it stopped looking really nice from the programming perspective. So what to do to make it less messy? Yeah, exactly. We need new functions. So this is needed because this is just definition of the system that makes system add body. Here we provide some information and add body. Yeah, we can put it also as a function, but it will be function create pendulum. Yeah, and this is the main goal of this script to create pendulum. So don't bother with it. Uh, this is for testing purposes, so I just leave it as it is, just for your reference. Same here. But here we introduce some procedure and it doesn't look so nice. Yeah, so I think that this should be one function. or we can use function kinematic analysis. Those are two ways to proceed. Yeah, because in practice we just want to make a kinematic analysis, just get Q and make it for the single time instant. The issue is that it won't really work, as we can see, because it uses here some that time is vector and then we have dt. So let's just make a new function. Yeah. Where it is evaluate, convert to function. Okay, so here I have the error that it won't work because we have an unused function that use some stuff from something else, so we have to do it by hand. So let's create a new function. So we will create for this few functions. Yeah. So kinematic analysis position. So this function will just do that part. So let's see what it needs to do this part. Yeah. And the main goal of this function is, it's good to write the goal of the function just to know what it's doing. So single step kinematic analysis on position level. Maybe not level, but level. Yeah. So let's see here. Yeah. So in practice, it should do this stuff. Yeah. So because we don't want this function to put anything, we just want it to provide us with the error if it is not working. Yeah. So now what we need for it to work, we need for sure Q0. We need system because it's here and there. We need to know Q0 at II, and we need, I suppose, TII. Okay. And the things that it will return, as we can see, the only thing that is not declared is QII, and now it's all green, so it looks pretty promising that it should work. Okay, makes sense? And because of we have already written it, I will put it here because there is no good reason to have the same code in two places. You do exactly the same, yeah. So it's programming mistake to leave the old code here because I create this new function that is sub function of this one. Makes sense because task is the same. And it doesn't matter that I want to use it out there. I should also replace it here for consistency. Make sense? Uh, so yeah, so that's why it will kinematic analysis position. Yeah. Okay. But it means that I can get back here to our pendulum and then just use it here. So I can put here Q0 because it's for us, Q0 because this is input, and T0 that was simply our t here. Well, I can put it 0. Remove all this. Run it. It doesn't recognize t because it's here. Yeah, and it runs. So good. Yeah. So one clutter less. So for sure, I don't like this line. Yeah, I do not like this line pretty heavily because it gets into our implementation details. Because as you have noticed, we are passing the system back and forth, but we do not operate on it directly here in the script. Yeah? This is user interface. Yeah. So of course, if you are a so-called power user, yeah, you might be aware of the how it is done under the hood. Yeah. But the user shouldn't care too much. Yeah. How it is done that, for example, those driving constraints are removed. Yeah. So I think that either we have provide here this function to remove driving constraints, or preferably we can just put all those three operations in single function that just do this. Yes, so that the function that just solves for us kinematic analysis for initial position. Yeah, makes sense. So so let's just write this one function that do all this. Yeah. So another function. Is it a good name? Initial kinematic solution or something like that? Maybe it could be better, but yeah. I don't know if here is. Okay, before I will find it. Because do I have here some useful editor open? So okay, so it performs kinematic solution on the position level to get coordinates consistent with constraints. Make sense? So of course the result of this function is a set of Q0 that is consistent with the constraints. Yeah. For sure we have to put here sys. Uh, so we can close all this, but the way it works, uh, it's a little complicated, but yeah, but we have to provide for sure initial Q. Wait, no, we don't have to provide initial Q0 because you can get it, uh, but we have to provide at least body name we have to provide the information here for driving constraints. Yeah. Yeah, it's a good question how to do this. And we have to solve it somehow. That the issue is that okay, there are a few issues here. Yeah? So first of all, how to make it nice for the user, because it's not so easy to write a algorithm that will guess where to put the constraints. We know that it's not on the ground, but on the other hand, it's easier for us as designer because simply we can take a look on the drawing, yeah, and then we know, okay, so this pendulum should be there at this angle. Uh, the issue is that that what it started getting to be a little overcomplicated. So I wonder if we should go this direction because now possibly you have to put many driving constraints if we have system with more degrees of freedom. So I think it's not worth. Yeah. So let's step back. Yeah. And get rid of this function and let's just write function that remove driving constraints. Yeah. So let's just add okay, because I click the file. Okay, better. So um, in practice, you want to remove all driving constraints. Yeah. So it operates on the system and it just do in our current implementation did that thing. And no matter how many driving constraints we will add, it will work. Yeah, because if you add more, we just put all them to 0. Yeah? If you add different types of adding constraints, we can just add them here as well. Okay. Uh, it runs. Maybe it's not the most beautiful. Still, we could work on it, but now there are just more minor things, and we have more important. So let's go further. Okay. Uh, so we have added here, yeah. And now we have to add, include alpha, beta in the system. We can do this. We can generate equations of motion and solve equations of motion. Okay, yeah. Uh, so let's proceed according to our to-do list. Do you remember why we need alpha and beta? What are those? So just in case, yeah, when we're talking about our equations of motions, here I just put a reminder of how inertia looks like, some forces, including gravitational forces, and so and so. And when we get to the final equations for the system of the constrained bodies, yeah, we were discussing that we will add those extra terms, yeah, from so-called Baumgart procedure. Yeah, so those are boundary terms that are needed here to stabilize our constraint. So they, when they deviate, yeah, they will get back to the proper value. Add them. Yeah. So we can simply add them to the system. Similar in the way like here we add gravitational forces. Yeah, so we can add them because they are system properties. Because then we'll just solve them. So let's add them here. Yeah. Uh, I call them Baumgart alpha and Baumgart beta to be because alpha beta is quite general term. You can refer to many things. So to know that at least after the name of the procedure or stabilization alpha, stabilization beta, we can also add. It's okay to call it Baumgart or if you prefer stabilization. Okay. Because we use these arguments here, as you can see, I have some errors that you cannot read. Again, I cannot read them even, so, but it's interface, yeah. I believe that they are there because, they complain that they are here not in this argument section because as we remember, when you put argument section, we have to put everything there. So let's put in there. So they will be scalar of tau double, and we can give them default value like 10, because why not? Uh, it's not here, but I pointed out that values like 5, 10, 20 are typical, are reasonably good, yeah. So we can add them here, yeah. And preferably they have the same value, alpha and beta, yeah. Okay, so they are here. Of course, I have some warnings here as a reminder that while I provide them, I give them the description they are not used by any way, yeah. So we have to store them into the system, yeah. So now now I call it vanguard velocity, yeah, because it's just alpha, but we need 2 alpha. We'll make this all the time, so I'll just store it as 2 alpha and don't bother with it later on. And the next one is position term, beta squared. Okay, okay, fine. Good. So the step is done. Include alpha and beta in the system. Yeah. And so we can provide them here like, I don't know, 50 and 50. Let's see if they will work. Yeah. Okay. So now we have to generate equations of motion for the constraint system. Uh, those are equations of motion for the constraint system. Yeah. Before we solve them, we have to get them. Yeah. So in the easiest term, let us just write a function that will calculate this q double dot. Yeah, we can make use of lambda or not for post-processing or not, yeah. But just to solve the system, we have to set up, this kind of ODs, and to solve ODs, we need accelerations. Yeah, accelerations, velocities, and positions. Yeah, so the easiest way to proceed is just write a function that will get us acceleration from all this equation. Okay. So to solve this, let's, like always, put it here, yeah, and then we will wrap it into the function. Okay. Okay, so equations of motion for the constraints multibody system. Yeah. So we have we of course have to provide left hand side, right hand side, and then solve it, and then extract acceleration. Yeah. Uh, so left hand side matrix uh, is the matrix. To generate this matrix, we need M. How did we get mass here? Uh, Assemble mass matrix, yeah. So first thing is diag of M, because M was a vector. And we also need, and the second term that we need is Jacobian. Yeah? So we need here CQT, here we need CQ, and here are the elements with the zeros. Yeah. So here we have to provide CQ transposed, yeah, and in the next line we have to provide CQ and zeros of what is the size of those zeros? How many zeros do we have here? Do you know? Okay, there are many indicators. Yeah. Maybe. Okay, but okay, CQ, the length of CQ is a little ambiguous term, yeah, but it must fit here, so it's the size of G. So, and so it means that the size of the constraints. It is this term. Yeah, I suppose that, yeah, and it's squared, so yeah, you just have to fit here, yeah. So it's the second dimension of CQ here, and the same second dimension of CQ here. So, or the first one, depending how do you count. But if we do to fit it here, for sure, this is just the number of the constraints, yeah. So okay, and this is our left hand side, yeah. uh, this is our B, so we have to solve for it, and now we have to get our right hand side, yeah. So to get right hand side, uh, firstly is just force. And then we get that one, yeah? And to calculate this, we need G, C, and CQ, yeah? So well, let us calculate this. So G is simply I don't know. Sometimes, as you can see, it's too helpful. Uh, so t0 equal to 0. So make it t0, then we'll fix it. And we also we have q0 from the previous step. Qd0 is zeros. Do not overcomplicate this of size of q0. Okay, so we have G here. Getting C is pretty easy. But now how to get C dot? Do we have function to get C dot? No. No, 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 no. Constraints dt gives us uh, partial C partial T, not C dot. But we can simply calculate C dot in one line, yeah, because I don't know if I have it here, yeah, maybe I don't have, but simply we have used it already earlier, so I will just write it here. And in practice, this is almost always 0, but let's leave it here. Yeah? So C dot is CQ times Q dot plus CT. Remember, there was this kind of equation. Hmm? Like, if you check, like for 2 or 3 or, few weeks earlier, yeah, for sure there was. Yeah, that's simply when you were scrubbing C dot, yeah. It's just partial C partial Q times Q dot plus what's left, it's only times, so partial C partial T. And then it makes it complete C dot. dc over dt. Yeah, so that's why we have this term plus this will be always in our case 0, but this is now the complete form. Okay, so now we have everything. Yeah, so we can write here G minus from the system we get okay, let's run it. So Baumgart position times position level is C. Minus sys Baumgart velocity times C dot. And okay, so here we have right hand side. Yep. So Fg minus this constant terms times C minus another constant terms times C dot. Works. And now we can solve it for Q double dot lambda. Yeah. So Q double dot lambda is simply okay. It somehow works. as we can see, we have zero accelerations for the ground and some non-zero accelerations for what? For the pendulum. Well, gravity is active, yeah, and we have all this into millimeters, so it makes sense because millimeters causes those are quite large values. And then here we have some those coordinates related to the lambda values are here that are related to our constraint forces. But we are mostly interested here just to solve it on QDD. And of course, QDD is just QDD lambda 1 to 1 to number of coordinates for our system. So those are our accelerations in our system. Make sense? In practice, we have done it. But now let's fix it. Okay, maybe not let's fix it, but let's just put it as separate function, yeah? Because now it's there, but it's not so useful. So this is the whole procedure, because here we just get values that I will add. So let's see if it's again complains about some stuff, but okay, so let's create a new function. Okay, better. Uh, should we call it get system accelerations or just system accelerations? And okay, I will delete it later. I think system accelerations is clear enough. Okay, returns acceleration of the constrained multibody system. Uh, so what we want to get, as name suggests, is we return QD, and to return this for sure we need system. For sure we need QD, and time to make it all works. Yeah. Do we need anything else? Let's see. I don't think so. Uh, so let us put here, yeah. So seek. So first we calculated left hand side. So mass from the system works. CQ Jacobian of the constraint system based on constraints works. This is another thing, yeah. So this is as it should be. F provides forces. G constraint vector based on Q dot and time. C constraints based on Q and time. C dot Q dot constraints of the system with T. So here we have all the things that are given. We calculate QDD lambda. We return okay, okay. There was just I got the message that it couldn't delete the file, but maybe because okay, whatever. Now it's gone. But okay, so we wrote this function. We fix hopefully all those zeros that we added here to just QD entity to be available. And yeah, now we can replace all that with that line. We have to go back here with those zeros because this is what is available in our workspace here. And we should get the same result if everything works correctly. Okay, it works. Any questions? Any surprises? So what we have just done, so after the math is ready, like here math is ready, we just have to put all those with understanding of what are those terms, yeah? We have just put them together. Yeah, and we have done it, calculated QDD, and now we can solve it for ODE. Okay, perfect. Okay, so I already crossed it out. Solve equations of motion. So now, as we have equations of motion, we can just solve them. Yeah. Here again is the same situation that we have some code uh, that do something. It's put it here, and it should be in the function. Yeah. So I won't even try. I will just create. So this is one ODE. This is quite generic one, yeah, because here, as you may remember, we have implemented Euler-Kromer method. Uh, and it's a little pointless that it's here. So I will put it into this function. Okay. It will have, for consistency, the same similar interface like kinematic analysis. So we will return positions and velocities. Um, However, because it's general OD order Cromer, so we won't get this based on system and time because it doesn't make sense. But what do we need to solve for ODE? Yeah, we need the time for sure. Yeah, uh, we need other function, or in our case is QDD function. Yeah, so function that returns accelerations. We need Q0. Yeah, we need QD0. Yeah, because we need those velocities somehow defined. We have to provide time, and then we should be able to solve it. Let's see if it works. Yeah. So this is not the part of our system. This is not a part of our system. Yeah. So it works that way, that here we have function that returns acceleration based on q, qd, and t. Does this make sense? And then, of course, q0 qd0 is initial velocities. Yeah. So okay, so here also we have that we assume that it's nicely spaced. So dt is time 2 minus time 1 number of times. So that way we can have q and q prime identified in that way. Then we can get starting solution. We can put so here we can just replace this with qd0, yeah, because we have supplemented this. This is part of the solution, so for sure it's not needed here, yeah. And then we have this loop. This is part of the solution, so also it's not needed, yeah. And here is the line that we get accelerations. So we just have to use our OD QDD fun here, yeah. And what is available to us, yeah. So here is interface, yeah. So it is based on Qn, Q prime n, and then the third one that is required is time, yeah. Time is not here, but can say that tii is time of ii. So tii, and the rest is just the algorithm, Euler-Kromer algorithm. So here we get accelerations, yeah. Based on accelerations, we can approximate velocities. Having velocities, we can accelerate positions, yeah, according to the Euler scheme. Then we store the results. Then we have those results for the next step. And that's all. Okay, makes sense? Uh, let's close it. Okay, we don't have to leave the MATLAB. We can go here. Solution of the ODEs using the Euler-Kromer scheme. Yeah, I think that I can remove it. You can still find it in the GitHub if you want it. However, I need the time vector. So this one is provided here earlier, so we don't want to get new assembly because it will be with the errors. Yeah, so uh, we can just use our new ODE function. And let's hope it works. So it will provide us q prime. We need to provide this function. This is given, this is given, this is given, yeah. So the only unknown from here is let's use many time steps, because Euler-Kromer is not the most precise method. Yeah, if you use all the 5 or the 15s or something like that, they are usually, you know, better than that one. But it should be good enough for our pendulum. And now we have to provide QDD function, yeah, and QDD function is given like that. No C. So it means that we need to provide anonymous function that returns stuff like that, yeah. And we have system acceleration function. And the difference between system acceleration function and this acceleration function is in that we need to provide system. That's why we create this here anonymous function. We have to remove those zeros to comply with this interface. And it works somehow. Nice. Nice. It's always nice when it works. It's often I don't know. Yeah, yeah. I program for quite a bit, so when I make so many changes and it works, it starts being suspicious. Yeah, but because it's here for the lecture, I try to be pretty, cautious and see how it works. So maybe it works even. Yeah. So hopefully we have uh, we have ended up there, yeah, but because we still have quite a bit of time, we should add extra term, yeah, our final task that we'll provide today, and this task is to verify the result. So our next goal is to take a look on this vector and check if all this makes sense to us. But of course, we won't analyze it by looking on those numbers because there are quite few of them, like 10,000. Yeah, so there is no point. Of course, we'll do this by making some plots. But let's do this after a short break. I propose to have now like a few minutes of break. Yeah, and we will just check this those results after the break. Okay, great. So we are back. So one thing to notice, after one comment from the room that here, let's add here 0, yeah. So here, this line just calculates acceleration for the system, as you can see, only at time 0. And I put it here mostly to verify, like earlier, that it works at all, yeah. And their solution looks pretty reasonably good, yeah. But now let's back to the our solution. So solution should be done, yeah. And now we should be able to make some plots, just from the for the and velocity, yeah, as well, and see if they looks reasonable. Yeah. So we can plot time and q, and for example 1 and everything, yeah. Well, no, as expected, yeah, because we plotted position x of the ground, yeah. So this is just for verification. We are not expecting ground to be moving, so it's not moving. So we can plot all three things for the ground. Perfect, yeah, not moving at all and not rotating. And now let's get to our pendulum. Yeah, so pendulum, this starts at 4, because this is just a second body, and we get something like that. Maybe line should be thicker, yeah. So let's do the trick with the line. Line wide and make it like is 2 okay. I think that we can even go with 3. Okay, we can. Does it look correct? Yeah, it looks pretty fine. Yeah. So we can check our Q0. That for our Q0, the initial value was 33, yeah, millimeters for X. So it should go as we expect. So it means that we have this pendulum that starts at this angle 30 degrees from the ground. Yeah. So we expect it, of course, to swing under gravity without any external damping or what, make this oscillatory move. And because we are not adding energy, the only force is gravity force, we are not expecting that it will to grow. So it should be bounded from this from 43 to minus 43. Then it looks fine, yeah. Uh, of course, to make plot nicer, we should put at least X label, yeah. Okay, let's see if it will work. Okay, so let's get to help. Okay, I wanted to change it because as you can see, this font is unreadable. I barely can see it. Yeah, maybe you can also see it. But, yeah, of course. Okay, let's see what are the good units. Are PT good units? So points. Okay, let's go with points. I will just check. If it works, I will leave it. If not, then okay, it works. Nice. Yeah, let's make it use some nicer font like that one. Let's okay, it started looking pretty good. Yeah, like for a plot. But okay, okay, so we I detour again. Yeah, but okay, this is still small, but it shows 43 point something, so looks reasonable. Yeah, so this looks reasonable, which is nice. We can go with that one. Does it look reasonable as well? This is Y coordinate. Yeah, local Y coordinate in the local coordinate frame. So the pendulum was below Y axis. Yeah, and the length minus 50 is the bottom part, yeah, because this was the half length of the pendulum. Pendulum has 100 millimeters, so it should get in y to minus 50. It makes sense because it starts from minus 25. It also makes sense, yeah. So looks as it should look like, yeah. And the angle. It's always hard to read those angles, yeah. So let's convert this angle to what? To degrees, yeah, because it's in radians. So it goes from this minus 30 to minus 50. Makes sense? Makes sense. Yeah. Because the same as it should swing, yeah, because it's left from this part minus 30, so it should also leave here minus 30. Minus 80 is of course 4 angle, so it should get to minus 50 and back in the same fashion, in the similar fashion like X goes. Makes sense, yeah. So this first checking looks fine, yeah. So most likely velocities also works fine. We can always take a look on the velocity as well if we want. Just okay. Hopefully it's fine. Uh, for sure, we can try to differentiate it numerically to check it. Hmm. Okay. So is it all that we can get from? Is there anything interesting that we can get from those plots as well? There are many stuff that we can calculate based on this, yeah. Uh, the most basic that I can think of is because here we just check the coordinates, yeah. Another thing that we can be interested is about, position, velocity. We haven't calculated acceleration, so but also it could be also possible to get acceleration of the arbitrary point, yeah. So for example, here we could get the position of the end point. Why not? Yeah. So this is one thing. Another thing that we could get here is just trajectory. Yeah, so again, we could calculate, instead of calculating those time x, time y, we can again show trajectory if this really go along the line. Yeah. Another thing that we could just directly easily calculate uh, is constraints, to see if constraints are met. Yeah. Uh, let's do it. Why? One reason is that, because I have told you that, if you do not use those boundary stabilization, typically the solution has tendency to diverge from the constraints. Okay, so I hope that I will be able to demonstrate it to you. That so trying to solve directly those equations after second differentiation of the accelerations will fail. Okay, can you check it? So it depends on it. Uh, so let's calculate C. Yeah. So let's calculate. So C is the matrix, will be the matrix. How we will put? We will do the same. Yeah. So the first coordinate will be number of constraints of the system, and the second one will be length of time. Okay. Yeah, because we have to store it. Yeah. Or let's put it. Because typically we see like a vector, so I just put this extra description just to differentiate it. Yeah. And now, of course, to calculate all this, we have to loop. Yeah. For t equal in time. Okay, we need index to put it in C. So e equal to 1 to length of time, and tii is equal to time of ii. Yeah. So we have to do some programming here. But okay, so now we can calculate that C is simply vector of constraints from our system. Q in our case is simply Q of everything at ii, and T is simply tii. Now we can store it at specific location. And if we get index right, we get C. Yeah. So constraint over time. So we can get this part, yeah. And here we can plot how specific constraints. Okay, no. Okay, it doesn't make sense because I tried to plot C, but we should plot C in time. Okay, now it's better. So uh, okay, I tried to put so because it's not working, so I try just to put, rearrange the windows, that on one hand side I will have, this code that I can change it, and on the other hand side the figure. but it seems that it doesn't like it, so most likely it will crash soon. But okay, yeah. So okay, I'll try to queue MATLAB if I will find it. Mm-hmm. Okay. And let's try to run again and do not make this kind of tricks with Windows. Okay, so we get constraint in time nicely met. Uh, Second one is also fine. Let's plot all of them. So as you can see, you can see how Baumgart works, by the way. So as you can see, we get some constraint violation. Yeah. And good thing that is always that this is pretty small. Yeah. So as you can see, it's in the range 10 to minus 3. So because we work in millimeters, so this constraint violation is in the level of some micrometers. So it's typically acceptable. Yeah. Uh, and yeah, so it's here. Yeah, so clearly there is some, error on the constraint. Uh, and now we can check if what will happen if we put here 0. 0, 0 means that we effectively turn off this Baumgart stabilization. Yeah, because if you put here those terms zeros, then all those extra terms, like here, those two terms will just disappear. So we'll get original formulation that I claimed without any proof that it's not so nice to be solved. So let's run it. Okay, and you can see this effect, yeah, clearly. That when we turn on this constraint stabilization, it works that way that when it goes out of the constraint, then it gets back closer to 0. So in some way or another, it's vibrates there. That's why it's called stabilization. But when we turn it off, as you can see, when it starts diverging, it just diverges, yeah. And as you can see, it diverges quite far because it diverges to the level of minus 0.25 or 0.15, yeah. So this is already quite reasonable. And it doesn't diverge so heavily, and one reason is also because we use quite fine time grid, yeah, because I also claim that this algorithm is not the most accurate because it doesn't, yeah, it's good enough for our use and simple to implement, very simple to implement, but it's not uh, so we can just decrease its accuracy like tenfold and try to run it again, and now we can see that uh, constraint violation it's already into range of millimeters. Yeah, so we decrease accuracy 10 times and we get 10 times the this deviation. Maybe we will be even able to see it here. Let's see if we are already able to see it here. Yeah, here we can see it. Like for example, here the peak was already at minus 42 instead of with 43, but here we can see the clearly it's higher. Yeah, So you can see clearly that our pendulum has moved. Yeah, it might be even better seen if we will plot not the position in time, but we will plot by CM I mean center of mass. Yeah, so if we plot the trajectory of center of mass of our pendulum, so now I have to fix the label, and because I fix it, let's add already y. Yeah, you can see that it's not really just a part of the arc. Yeah, so grid on axis equal. So yeah. So it's not what it should be. Uh, will stabilization alone fix it without improving the time grid? So firstly, yeah, so as you can see here, we have quite few variables. So let use those, use equal to 10. Um, so still we get violations at the range, at the bigger range, 0.1 kind of. So let's plot this trajectory again. Yeah, so we can see that it's better. It's far better, yeah, because it's not so visible here, but here still there are some double lines, yeah. So we can fix it either by improving the accuracy of our algorithm, because then with the smaller steps we get the better accuracy, so less drift, yeah. Maybe we can also put here larger number, because those numbers like 5, 10, they sound like they're good for range of meters, but we are in the range of millimeters, so let's see if it improves something. And here, if you remember the numbers that we had, yeah, those are already much smaller. So if here we have smaller constraint evaluation, so of course our trajectory should be also more precise. And I hope that you see that it looks better. Yeah. Uh, of course, if we zoom it, we can see here two lines, but as we can see, because of the scale, they are quite close to each other. Yeah. And at least the good thing is that so let's make again while about this without constraint stabilization, if we allow this trajectory, even if it's small, yeah, if you allow it to run for a long time, yeah, it would end up totally different place, yeah, because as you have seen, it has tendency to diverge, yeah. And here, even if you run it for a longer time with constraint stabilization, while it might not, just go precisely along the line, yeah, it will be always close to it, yeah. So it shouldn't get, let's say, thicker plot, yeah. Make sense? Because we are in the range of millimeters, maybe we can even add those two zeros. No, no, for sure not. So now we are over exceed, yeah, the specificity, as you can see, some issues with conditions security, so that that we get too far with those parameters, yeah. So yeah, so that's why they should be high enough, hopefully, to get reasonable solution. But if we go too high, like here, we get into numerical issues. So it also doesn't like those values. Uh, so let's stay with the range of 100. Yeah. So of course, so again, if we go to 0, 0, and we will increase here time to 10 seconds, it started getting really far. And now, no, no, no. Now, oh, now this trajectory looks really nice. Yeah, you can see that it's at the same time it's swinging, but it's also moving sidewise. Yeah. So let's put those 100s here that we have been used. So again, a lot of swings because time is much longer, but they are bounded. So if we plot a trajectory, it looks the same. Okay, any questions? Okay, so should we end up today, or do you want to see something else? We could plot also energy of the system, but it's a little involving, yeah, because for the energy we have to kinetic energy is pretty easy because it's just this one squared qt m qt, yeah. But we have to also include the energy of the system. It's also not so complicated because only here you have gravity, but still we have to calculate it. So it would be possible. Uh, yeah, we can find it into the literature, but yeah, it's possible pretty reasonably to calculate the energy for the, because of the kinetic energy and the potential energy due to gravity. It's just, displacements of them. In practice, this is just we can calculate it almost by hand, yeah, because it's just a displacement of the center of the mass with respect to y-axis, yeah. Uh, but still, and then that it's constant, and that's all. We could also calculate those forces, see how those reaction forces works. So there are, many things that we can calculate, or just as said, we can calculate the position of arbitrary point. But sure. But those are I think the most important part, yeah. Like how the constraints looks like, and then they because this is one of the one of the way to show that system at least works reasonably well, and also how this works. I mean that one. It's up to you. Yeah. Uh, it's not needed because you simply uh, can put it here as well, because this is just a simple for loop. So you have to create a system, then you have to add ground, and then from because it's still not so many bodies. I would put 4 because like for me it's just easier to make 4 and then put this n equal to whatever, yeah. So I would make 4, yeah. So I would make that, assume that n link is equal to, for example, whatever 100, yeah. Most likely not, but on the other hand, if you make this loop, why not? and then write that L is equal to length of body is equal to L by 2 by n, of course, yeah. And then for n equal 1 to n, I will add the body to previous body and the next body. I will add body with name body I or link I, yeah. So you have to because the names should be unique, yeah. So you have to concatenate this with the string to num with the representation of the number. So body 1, 2, 3, 5, 100, whatever, yeah. And then so ground could be body 0 to make it easier calculation. And then you have to add revolve joint between this body and previous body, and you have to provide the location, yeah, and the location of the joint for each body except of the ground will be so let's say that this is body and this is next body. So if you add this body, you have to connect it with the previous body, yeah. So this would be body 1 connected with body 2, yeah, and the location of the revolved joint will be in this body 1. So previous body it would be most likely like length of the link by half 0, and here length of the link by half minus and 0, yeah. And then you can also add this spring element here. So I would make it for a loop in for loop because it's like 4 lines of code, yeah, instead of whatever number of links is there. Yeah. Yeah, so you have to add this new force because it's in practice this is torque applied to both bodies. So you have to add torque function, yeah. So you have to add function like we don't have here functions for the forces, but you have add something like add, you know, like to make it sense, it should this torsional spring. So like here we have add revolved joint, yeah. So add torsional spring, yeah, and to system of course because you have to store it in the system. Then body I, body 2, yeah, and because torsional stiffness it's torque, and torque as we have seen on the slides, uh, like for example here, just torque is torque. So torque is not related to any kind of location, so you don't need to provide any SE vector. SE vector is useful, will be you needed for the single force, that is another element that you have to do. So to add this torque, for the spring you have to know body I, you have to know body J, because you have to apply torque with opposite signs to both those bodies, and you have to provide stiffness of the spring, that will be radians per Newton meter, yeah. No, Newton meter by radians, yeah, Newton meter by radians, because yeah, this is the stiffness. And then you have to provide initial angle between those bodies, relative angle when that will make this to torque equal to 0. Here, of course, it will be, of course, here it will be most likely 0 if you would put line in, put all those bodies into the line and put all those coordinates at 0 angle. Also, the relative angle between those two bodies will be 0. Yeah, and then so so like we have done with another stuff. So firstly, you need this function that accepts system, body I, body J, and the next one would be stiffness, spring stiffness, and the last one would be what? This initial angle, yeah, yeah, relative angle, yeah. So phi 0 relative, yeah, something like that. Uh, mm, Then you have to define this kind of the structure for this force that I think that should store simply, body index, and then this those two values. Yeah. Then, of course, you have to add this to the system. So you have to go back to the make system function and add something like sys forces torsional spring is empty. Yeah, like we add here with the constraints, and to make the space to keep the information about your force for the torsional spring. Yeah. So after those two steps, though, so adding here empty container for the spring, you could write this function to add torsional spring to define it and add it to the system. And the last thing, okay, there are still two more steps, but it was always like that, yeah. So the next step is to put here somehow the force, because you have to add, after you add this to the system, you have to express it, yeah, in the function, in the form of f. So here, the easiest way would be to write it here. So here we can write that for torsional springs, all the torsional springs, you will add those forces in correct indices, yeah? And you know that you have to get here K from the definition, which is the stiffness, yeah? And then you have, because you have body indices, one and two, in practice you don't have, now I can see that you don't need all indices, you just need the indices of the angle. Makes sense? Because here you have to read one angle at second angle, because the torque that is applied is simply stiffness times difference in the angles, yeah. So stiffness times angle 1 minus angle 2 minus angle 0, so this initial angle, it's your torque. And then for force, for body I coordinate of the angle will be this value of the torque, and for body second will be negative value of the torque. Like for torsional spring, you have to just find a neutral angle. This is already physics. So so simply this is the angle at which you assume that existence of the spring doesn't produce any torque. Yeah. So almost like it's at when they are connected in the initial state, so 0, 0. And I think that this is just valid assumption for this task. Yeah, because we assume that the beam, like the physical beam, if you have this continuum, if it's here, if it's straight, totally typically is undeformed. Yeah, so there's no stiffness. There is just small stiffness due to gravity. Gravity existing. Here we have no gravity, so it should be straight. Yeah. Yeah, exactly. Yeah, but initial must be constant. Yeah, for the angles, yeah, because if, for example, you have here 0 and this will bend, yeah, so the angle will change between the bodies when you calculate the torque, because you need this to calculate the torque, and this is how this is. It clear? And the first test is that if you run this simulation and provide no forces, there should be no motion. Other test that you can for example add some initial displacements, some small displacements, yeah. For example, let's say that, of course, okay, I would start with the single body with like our pendulum, just put it horizontally, or even not, yeah, whatever, yeah. Okay, so for example, if we were just take our pendulum that we have done, get rid of gravity, and put here torsional spring, what you would expect this kind of the system to work? Yeah, no force. Hmm? So let's say that this is our system. It's very similar to our system because in practice we have done this pendulum. Yeah, just remove this force. Well, how this system will behave? No, no gravity. It won't be fixed because the system is already deformed. So it will oscillate. Yeah, it will oscillate back and forth along this angle. Yeah, maybe I don't know. Maybe you just didn't get that it's deformed. Yeah, because if this would be the initial state, of course, then it won't move. Yeah, I assume that initial state is like described earlier that it's horizontal. Yeah, so if initial state is horizontal, but still you say that this angle is 30 because why not? And solve it that way, then it will oscillate. Yeah. So in simple terms, if you use, for example, already the code that we have done here, yeah, get rid of gravity and add this spring and put that spring initial angle is 0, uh, and you make the calculations right, yeah, with those signs for the torque, so this is also good to check for it, then it should just oscillate back and forth. So for example, this is the very first test, yeah, because yeah, yeah, so because our solver is physics based, yeah. So everything that makes you are expecting to behave from the physical system, it should behave that way. If it's not behaving, it means that either model is wrong, implementation is wrong, or just yeah, something like that, yeah. But models are quite simple here, so they are most likely right because this is just linear spring, nothing fancy. So just there's so if the system is not behaving in the way you are expecting, so either you make some mistake here in this definition, or this is just mistake in the implementation. And the best way to test your implementation is on the simplest example that you can predict pretty exactly how they behave, yeah, like we have done with the pendulum. Yeah, so that's why we make the similar pendulum, because if we use this same model and we apply it to slider crank, of course it will move somehow. Yeah, but motion of the slider crank according to gravity is pretty, it's not so obvious, yeah, how it will move, at least not for me, because the bodies will make some pretty can make some pretty complex motion. Of course it will go back then, yeah, but here with the pendulum we know that it must go from this angle to this angle. You cannot say it easily for the slider crank. Yep, at least I would do so, yeah, so to make it consistent. Yeah, so here okay, so firstly here uh, here is equation. Yeah, so from this equation you know that to apply single force to the body you have to know body index. So because you apply it to one body, you have to know value of the force, and you have to know this vector, and you have to provide it. Yeah, so this is this SI local, yeah, SI local body I name, and you have to provide definition of the force. And as I told you, maybe you remember, maybe not, but I think that it's better to provide this as a function of time. Yeah, so we can just provide this as a function of time that returns two indices, 1 and 2, yeah. And then the same procedure. We have to add, preferably add function, add a simple force, yeah, with the indices that it's almost like driving constraints that you add it to the system, but the name uh, today you don't have here SE local, but you need this SE local, and you also need this force function. You don't need very derivatives because it's just the function. We don't calculate. The derivatives are needed only for constraints in this approach. Yeah. So this would be what you need for this function. Next, you have to get body those indices to know where to put force and where to get just where to put force. Yeah, because you don't, as you can see here, there is no. It does depends on the coordinates. Yeah. By the way, it means this is a little tricky. Yeah, because as you can see, it will work for small deformations, but it won't work in general because there are two. Do you want to hear this? Okay, so you can use this equation despite it won't be the most accurate approach. And simple reason is that, uh, as you can see, this force is constant in global frame. It will work because we assume that the angles are small, yeah. But if and the expression of the force that you have seen is in practice in local frame. But now you still, so sometimes you have to transform this. But you still need coordinates. You need coordinates to make this transformation to global S. Because whatever you will tell about the force, if it's global or local, no. Okay, so my mistake. Once again, force, this it's okay. Sorry about the confusion, but again, every term like this force is in global frame. Yeah. So if we assume that F is provided here, as you can see, this force is in global frame. So it will occur for this task, yeah, because this is in global frame. So it means that no matter how those bodies will rotate, move, or whatever, the force will always have the same orientation with respect to global body. Yeah. Of course, this vector S will change. Yeah, because it is typically defined in local body because it's constant, which makes sense. Yeah, but here you have to transform it to global because description should be consistent. This must be in global as generalized force because all equations are in global. Force will be provided in global, so you don't have to transform it. But SE local will be in local, so we have to transform it. Yeah, so in practice it will be omega times A I times SI local. I hope that you know it. Yeah. So yeah. So to add this force, you have to add force here, add single force, make space in the system to have a place like here to edit where. Then implement it into the forces. So for single forces in single forces, add them to the force vector according to this equation. And then when you will define the system, you have to use this function by adding it to add it actually to the system to be included in all the calculations. Yeah. Okay. Uh, Anything else? Okay, I cannot see any comments from the audience. I hope that YouTube is working. It should because I have no errors. So yeah. You mean what computation? The value of it? Then it's totally up to you. because the system doesn't care. We just have to provide a number. Most likely here you will came up with some simple equation for how to calculate it, yeah, and then you can just use this simple equation based on n, or just put a number, yeah, whatever. Okay, so if this is all, so thank you for today. So again, the next week, let's organize this kind of Q&A session, and that's all. Yeah. If there are any doubts, yeah, we can address them. Okay, thanks. Thank you very much.